Okay, welcome to our second episode in the series, looking at the different topics in heliophysics that might be of interest to the general public. Keeping an eye towards sort of the big questions that NASA has in heliophysics. You know, we like to think in terms of big questions and what we can do to resolve them. What causes the sun to vary is a very large question that we study. How does the Earth and the heliosphere respond to these changes, and what are the impacts on humanity? So these are the so-called big questions, and they form the basis for what we call the framework for heliophysics education. You can have a look at the framework by going to this URL. This particular way of connecting heliophysics research into the national science standards is by way of, for each of the big questions, we have three subsidiary questions, and these generally are directly connected to the national science standards, which are referenced in the parenthetical information at the end of each of these secondary questions, or guiding questions, as you might call them. Today, we're going to talk about the sun is active and can impact technology on Earth via space weather, because we're going to look at the issue of is there a solar superflare in our future? Now, you've probably all heard about ordinary run-of-the-mill flares. I mean, those tend to be very exciting when they happen, and often the news media reports on some of the major ones. These are actually quite common, especially now during this year, which is the solar maximum year. But the question is, well, let's see, I think this is actually an animation, so let me run the animation. Well, there goes a flare. Generally, it's an outpouring of material from the vicinity of the solar surface, and usually it's accompanied by a flash of X-ray energy, plus a lot of heating of the local plasma, which then gets ejected and flows along magnetic field lines and does some really pretty interesting things, as you can see in this sort of edge-on view of the limb of the sun. These flares, these large X-ray outbursts, tend to come roughly in alignment with the sunspot cycle, which is the 11-year cycle of lots of sunspots and then no sunspots and then lots of sunspots again, which we've been looking at since the 1700s and tracking them, and it's about an 11-year cycle. These flares happen roughly in keeping with the phase of the sunspot cycle. When there are more sunspots, there are more locations where X-ray magnetic energy can be released in the form of X-rays and flare events. However, the really enormous flares, they seem to come almost any time during the sunspot cycle. Those are the little green bars that you see at the bottom. They don't wait for sunspot maximum. They come even very close to sunspot minimum sometimes. All you need is a magnetic field that's particularly tortured and is trying to release its energy. And this can often happen even during very close to sunspot minimum. Clearly, you do still need sunspots, because those are places where the magnetic field of the sun is amplified. And when you have sunspots that collide with each other, very often they collide with opposite polarity. That produces a lot of release of magnetic energy, and then you wind up with a flare. So you need at least a few sunspots on the surface of the sun to sort of produce these really big X-ray flares. We like to gauge X-ray flares in terms of what's called their fluence, that is the number of particles per second per centimeter squared, or just in terms of their X-ray luminosity. We grade them according to CM and X, CM and X scale. If C is a unit 1 intensity, M is 10, and X is 100. And if you ever hear of an X5 flare, that's 500 times as bright as a C1 flare. So there's a little bit of terminology here. You know, you should think of this like the magnitude scale for stars. It's visual magnitude 6 is a very, very faint star that you can just barely see with the eye. Magnitude 0 and 1 are really bright things like currently the planet Venus in the sky, or very bright stars. The difference between a magnitude 6 star and a magnitude 1 star is 5 magnitudes, which in terms of intensity is exactly a factor of 100. So between C, M, and X, you also see there's a factor of 100 difference in brightness. X is 100 times brighter than C. So if you imagine X as the brightest star you can see in the sky, C would be like the faintest star that you see in the sky with the naked eye. So it's a kind of a similar logarithmic scale. Let's see, we just saw a nice flare. The largest of these solar flares usually emit lots of X-ray radiation. That's a dead giveaway that you have a really brilliant, very powerful flare going on. And you can see the way I look at this graph here, which shows the frequency of flares of different brightnesses. The C-class faint flares are very common, and they actually do follow the sunspot cycle more or less pretty well. The M-class flares, they actually don't follow exactly the sunspot cycle. There tend to be more of them after the peak, after sunspot maximum. So actually, the peak of these fainter flares it is still going to be like a year from now or so. And then after that, they're going to fade out during sunspot minimum, and then you'll have very few of those. The X-class flares are the ones in purple, or rather the ones in red. And you see those little histogram bars, you know, they're sort of spread throughout the sunspot cycle, as I said before. So you can find one of these really powerful flares happening every year or so on the surface of the sun, almost regardless of, you know, the phase of the sunspot cycle. Another thing that comes out of these very powerful X-class flares is that sometimes they produce ejections of mass. They deliver enough energy into the local plasma and to the corona that they actually produce what are called coronal mass ejections. These are billions of tons of plasma that are shot into interplanetary space. And here's a nice video of that kind of a phenomenon. These CMEs are launched from the sun perpendicular to where the Earth is, so they are completely harmless. They're going in a completely different direction than towards the Earth. However, one of them, as you saw, expanded almost around the entire disk of the sun. That means it's actually coming directly towards you. It's like you're looking down the barrel of a gun, almost. So we call those halo coronal mass ejections, and those are the ones that we're the most concerned about whenever they occur. The interesting thing is that halo coronal mass ejections, they can occur on the back side of the sun or on the front side of the sun, and they look almost the same. So you can't tell just from seeing a halo whether it's coming towards the Earth or 180 degrees away. It turns out that a very good way of determining that is that usually these CMEs, the very big ones, they're accompanied by an X-class flare, which you will see on the front surface of the sun. And so if you see one of those, you'll know that that CME is headed directly towards the Earth because you saw the X-class flare that probably launched it. If you see a coronal mass ejection and no X-class flare, likely it's on the backside of the sun and you don't really have to worry about it. So there are, a couple of rules of thumb that you develop over time studying coronal mass ejections and X-class flares that the space weather community uses. Also, it turns out that the X-ray light from the flare on the front side of the sun actually gets a little bit absorbed by the colder gas in the coronal mass ejection that's coming towards you. So it actually dims the X-ray light a little bit. And that's another dead giveaway that there's actually plasma that's en route to the Earth or in our direction. Right. The occurrence of CMEs does follow the sunspot cycle pretty well. So that means that not only X-class flares, but also M-class flares and C-class flares on occasion can be the sources of these things. If it were only X-class flares that produce these, that gold curve that you see there, or rather that blue curve, would be shifted away from sunspot maximum, or it would be flat because all X-class flares would produce them for the most part. So, the fact that you see, a super flare or a flare on the sun doesn't necessarily mean you'll have a CME, but it can be used as a rule of thumb if you take into account the frequency of when these things occur during the sunspot cycle. And they become a pretty good indicator of what's going on. Right. As I said, the most powerful X-class flares tend to produce coronal mass ejections, but not always. And that's because the ones that are on the backside, you don't see the X-class flares. You only see the ones in the front. So that means half of the CMEs that come towards us, you don't see the associated X-class flare because it has to be on the Earth side of the sun in order to see the X flare. So, it's a 50-50 sort of a game. If you see a halo coronal mass ejection, it's a 50-50 game whether or not it's headed towards the Earth or directly away. So you have to use additional information to sort of make that fine-tuning prediction. Now, you can look at the X-class flares and how they're associated with coronal mass ejections. And what you find is, again, I said that the X-class flares are the boxes, the square, the diamond-shaped boxes, and that's the sort of the flare magnitude. But there are some that are not associated with coronal mass ejections, even though they're on the sun side, the Earth side of the sun. So there is a real complicating factor here. We're not quite sure exactly how these X-class flares translate into coronal mass ejections. There seems to be some other kind of physics going on that we still have not really accounted for properly. For instance, among the Earth-facing 42 X-class flares, 9 of them had no associated coronal mass ejections. So it's still a pretty good rule of thumb that if you see an X flare, you'll likely see a coronal mass ejection or vice versa, and you'll only be wrong like 9 times out of 42, which isn't bad, unless the one of the 9 happens to be the one that does some devastating damage to the Earth's technologies. And then you basically missed using X-class flares as a predictor of whether something bad is about to happen. So it's a little bit troublesome. There are also things, flares that are actually called erupting prominences. And these are plasma material that's launched from the surface of the sun or close by the surface. It goes out into space, but then it falls back onto the solar surface, and it never reaches escape velocity, unlike coronal mass ejections, which do reach escape velocity. Here are a couple of really good ones. This is the so-called Skylab flare, actually called an eruptive prominence. That's the correct term for these. Then there's also one in 1946, which is a massive erupting prominence spotted with ground-based, telescopes, and that basically artificially eclipse the sun's disk, so you can see faint things going on near the edge. So erupting prominences are actually quite common, especially during sunspot maximum. The solar surface is very active with magnetic fields being twisted around and launching plasma into the immediate vicinity of the sun, but generally not too deeply into the corona because the material does not have escape velocity, so it doesn't really get up that high. But compared to the diameter of the Earth, I mean, the arch that you see here, if you put the Earth to scale, would be about 10 times the diameter of the Earth above the surface of the sun or thereabouts. So, they get quite high. The biggest flare that we know historically occurred in 1859, called the Carrington-Hodgson flare. It was quite spectacular. It disrupted telegraph and compass and a variety of other technologies that we had at that time. It was a worldwide event, seen all the way down to the equator with brilliant aurora. Um, it's an amazing idea that if you were in the southern part of Florida or even Cuba, you would see a bright red sky from the aurora that were produced by this event. So they do happen from time to time. We haven't had an event like that since, but the thing is that we know a lot more about the record of these things. Um, we know that, for instance, the the flare that produces these coronal mass ejections also produces essentially streams of very high energy particles. And if the Earth is in the way of either the coronal mass ejection, or these particles, they enter the Earth's atmosphere and cause chemical changes. They essentially increase the amount of carbon-14 that you find, and that gets ingested into plants. And what you then wind up with is, instead of a normal carbon-14 level for a particular period, you see a spike from the carbon-14 produced by the solar radiation event. We've been able to find quite a few of these. There was one 660 BC, another in 775 BC, current era, and 994 current era. So they do happen. They happen more often than we actually thought they would. Here's an example of the carbon-14 levels. And you see these, the 775 AD and the 994 AD events. You can see those as spikes in the data. And that's how they're detected. There was another one that was discovered using even older carbon-14 data that occurred about 14,300 years before the present, and that produced an extremely large spike. So that was a really big solar flare that had real significant effects on the chemistry of the atmosphere. So we can actually track down these historical events by their carbon-14 anomaly. And so basically, it seems that these events happen really quite frequently. It's not just the Carrington event, but there have been a string of these things going back, 15,000 years. And so we can sort of figure out from when they occurred, we can get a rough idea of how often they occur.
Okay.
And we can rank them according to their intensity to get an idea of their strength. Okay, and we see there have been quite a few of these events, some that I mentioned. And they're quite a bit more powerful than the Carrington event, which is the one on the far right, which barely makes it onto this scale in terms of the carbon-14 anomaly that it produced. So these events you could properly call superflares. If you want to call the Carrington event a superflare, then by golly, all of these are 10 to 100 times more intense than the Carrington event. And we have a rough idea of how often they occur. So now the question is, if we take all of the statistical data and combine it together, what can we say about the frequency of these events, these superflare events for our particular sun? So what we look at is the probability that we're going to see an event that's stronger than a particular level. And we've seen 10 of these major events in the last 10,000 years or so. So that works out to a super Carrington event about once every 1,000 years. You can argue whether or not we're overdue for the next one or not. These don't come with a particular set period. So essentially, they come sort of in a random time interval. So, but the rough average interval is about 1,000 years. We just had a Carrington event back in 1859, which was 150, 170 years ago. Um, Now, does that mean that we have to wait like another 800 years before, on average, we're going to see another one of these events? Well, statistically, that's about what you would expect. But that doesn't mean that you're not going to see plenty more of these Carrington events. Okay, Carrington events are very weak, and they're actually hard to detect in this carbon 14 data going back, using the data going back 10,000 years or so. We really only see the really big events during that time period. So we actually don't know, if the Carrington event is a separate class, which happens much more frequently, maybe every 200 years, or if it's part of the same sequence as these superflare events. So, we don't know. Is the next one going to be in 800 years, or is it going to be tomorrow? um, the We can ask, for instance, looking at all these superflare events. Well, on the broad scale of the evolution of the sun, say over the last 5 million years, how typical is our current era in terms of producing these superflare events? Well, you can actually do an estimate of this. You can do a statistical estimate and work out from the carbon 14 data and also from tracks that we can identify in mineral samples on the surface of the moon. We can actually detect the tracks of these energetic particles as they go through mineral samples. And if you do a fine section of one of these mineral samples and then stain it, you can actually see the tracks and count them. And you know that the rock is probably about 5 to 10 million years old, given its geologic location on the surface of the moon. So you can work out really how often you should expect to see, or how typical the current era is. We know roughly what the radiation is on average from the sun during the current era and the number of storms that we see. And you can compare that to the average number of these tracks that you see over this span of 5 million years. And it works out that basically the current era is not that much different than it's been for the last 5 million years. There haven't been any dramatically bigger storms than the ones that we can actually see in the carbon 14 record, because if there were a lot more of them, then they would increase the number of the sun would have increased the number of these tracks that you see in the mineral sample over this period of time from these very big superflare events. So that's comforting to know that the sun has been kind of behaving the same way for the last 5 million years, and we're not really expecting statistically it to change all that much. Now, just to give you an idea how powerful these historical superflares are, the 774 AD event, it ranged in energy from 10 to the 34 to 10 to the 36 ergs. And that would imply on our flare scale either X3000 or X300,000 as an X-ray flare. That's just an amazing, the strongest thing that we've ever seen. Carrington event is estimated to have been an X45, and the November 2003 event, which is the biggest one we've seen during the space age, was only an X35. So this 774 AD event, X3000 is the lower limit and X300,000 is the upper limit to how strong this was. So this is a devastatingly bright, intense flare that would have done substantially more damage to our atmosphere and to ground-based systems than what the Carrington event did, which was a much fainter and much weaker event. So that's a little bit troubling. Luckily, as we said, these superflare events seem to be maybe only once every 1,000 years or so on average, statistically. So we have to hope that we're not in that unlucky part of this random series where the next one is going to happen tomorrow. Because if it does, our technologies in space would not survive an X3000 event. It would not survive any of these historical superflare events that we've seen. In fact, the Van Allen radiation belts would disappear for many, many, many months at a time. The upper atmosphere chemistry would change. It would be just amazing, an amazing thing to go through. But I'll get to that a little bit later on. We can go a little bit deeper in time and look at our sun, the activity of our sun today and during this period that we can sample with the carbon-14 anomalies. And we can look at other similar types of stars like our sun. Our sun is a G2 main sequence star. It turns out that the Kepler spacecraft, in looking for exoplanets, studied 56,000 stars that were similar to our sun in spectral type. This was a 4-year series of data that was taken on all of these stars. They were monitored for 4 years. And basically, Kepler was able to see, or statistically was able to see changes corresponding to basically 10 to 10,000 times a typical solar flare that we see on the sun. You can see the brightening of these stars due to a flare event, and basically calculate, count how many of these events you see for a particular star and for the entire ensemble. Now, the interesting thing is that if you look at 56,000 stars similar to our sun, and you're looking at them in a period of about 3 billion years time in their evolution, so that they're very similar to our sun, you can actually work out that it's equivalent to looking at our sun for 220,000 years continuously. So we can look not at the carbon-14 record to see how many superflares we get, but we can actually extend it to 220,000 years using these Kepler stars. And so now what we do is we count how many of these superflare events we see on these Kepler stars, and then we can do an estimate for how often we should see the same things over that span of time for the current sun. Now, here's what we have. Surveys of other sun-like stars. We're able to sense energy changes of 10 to the 26 to 10 to the 29 joules. And as I said, that's equivalent to observing the sun for 220,000 years continuously for that many Kepler stars examined over a period of time. We can do the math to see how that works out. And here's what the math kind of looks like, using a human as an example. You observe a family of 5 humans for 1 year, and a human has a lifespan of 100 years. It's your observation for 1 year is equivalent to looking at human evolution or humans' lifespan for about 20 years. So that's a pretty good chunk of a person's lifespan that you're able to look at statistically just by looking at 5 humans for 1 year in this kind of a sample. If you looked at the same family of humans for 2 years, then you're equivalently looking at the lifespan of a single human on average for about 40 years. So now you're getting to a substantial fraction of the actual lifespan of a human. So that's how that calculation works out. Doing the equivalent thing, you're looking at the sun-like stars in age similar to our sun, which is about 3 billion years or so, sort of give or take. You're observing 56,000 of these stars randomly across 4 years of time, which is the lifespan of the Kepler mission. And if you do that math, you get a number that's about 213,000 years. Well, that's close enough to 220,000 that I'm pretty happy with it. And that's sort of how you do this statistically. You take a large sample of stars, you figure out what their average age is, and then you observe them for a period of time, and you're able to deduce from that what the average properties of a single star would be over a period of time that comes out from the statistics. So that's a kind of a clever way of doing this. So we do this for these Kepler stars, and we're able to essentially observe what our sun would be like on average for about 220,000 years. And so for these Kepler stars, we count the number of flares that we see, and we come up with a distribution. And that gives us a frequency of seeing, on average, the same types of flares on our sun over a period of time. So here's what we do. All of the Kepler data is combined into essentially a logarithmic, a log-log plot. The vertical axis is the flare energy in ergs. And the horizontal axis is basically an indicator of essentially the area occupied by this flare event on that star's surface, give or take. What you notice is that a lot of the Kepler events cluster in the upper right part of the diagram. That's the observational effect because we can't see anything fainter than 10 to the 33 ergs in this Kepler sample. So that's the bottom limit to that cloud of points that you see. And the upper limit is sort of the brightest variation that we can detect on these stars during the sample period. But the stars form a little cloud up there, and you see that our 1774 event kind of falls in the middle of that cloud. Well, that's kind of neat. Oh, by the way, that cloud in the bottom left, that's typical solar flares that we see on our sun. So you can see that the sun typically produces a very different population of these flares than what we're seeing with the Kepler stars, because we're seeing only the really brightest flares for the Kepler stars. So we're sampling sort of the extreme edge of the flare intensities, and that's why we call these Kepler events super flares, because if you look at the y-axis, the average intensity of the solar events is about 10 to the 29 ergs, but for the Kepler events, those are 10 to the 30, about 10 to the 33 or 10 to the 34, or rather 10 to the 35 ergs. So we're talking a factor of, well, let's see, that's 30. We're talking about a factor of 1, 2, 3, 4, 5, about 6, almost a million times brighter, 100,000 to a million times brighter than an average solar flare. That's what these Kepler flares look like. And there, right smack in the middle of that cloud, is our 1774 event, which is why we call it a super flare. And it's also neat because we can compare it with these really bright Kepler flare events and do the statistics to actually find out how frequent events like the 1774 event are for the ensemble. And we can translate that back to understanding how the sun is producing these events and how frequently. What is found with looking at these sun-like stars is that, first of all, as stars get older, they tend to slow down their rotation. And by slowing down their rotation, convection tends to be more sluggish. The production of magnetic fields on the star's surface tends to be less violent and essentially less effective. And so you wind up with the activity on the surface of the star tends to decline over time as the star ages. It turns out that you can look at the rotation periods of these Kepler stars. You can look at each of the Kepler stars and measure its rotation rate by using Doppler information to figure out the rotation periods. And when you compare that against essentially the fraction of all Kepler stars that have those rotation periods, you see that the most active stars tend to be rotating, once every 15 days or so, which is much faster than our sun, which is more like once every 25 to 30 days, give or take. So these Kepler stars that produce the super flares, they tend to be very fast rotators, and also that means they tend to be younger than our sun on average. Young stars are still settling down, and they're still rapidly rotating for the most part. And they tend to be much more active in producing X-ray flares and a variety of other features on their surfaces, which makes them very active as stars. Uh, our sun seems to be sort of in a different category. Instead of the flares that the sun produced being related directly to the rotation period of the sun, they seem to be related to some other kind of phenomenon that goes on that's much less effective in producing flares. So that's the good news. The good news is that if these G-type stars observed by Kepler really are similar to our sun overall as an ensemble, our sun is sort of on the older side of that population of stars, which makes our sun less able to produce these superflare events. I mean, that's a fantastic piece of news. All right, that means that we don't have to worry about these X3000 and X300,000 events. Our sun is basically too old and too inefficient in producing the necessary magnetic fields and the necessary energy to produce them. So that's one thing that we learned from the Kepler study, and that I think is one of the most exciting things that we learned. It just goes to show you can look in different ways at the stars that we can observe in the sky, and you can learn an awful lot about our own sun in a statistical way by studying these other stars. And here's one practical example. You know, we don't have to worry too much about these superflare events. We already figured out from looking at minerals collected on the surface of the moon that our sun basically has been behaving the same way for the last 5 million years, you know, and it's a pretty, you know, it's got a couple of really big events that happen, but nothing as big as what we're seeing with these Kepler events. Now, you know, you can do a lot more, a deeper study on the Kepler data and sort of work out exact frequencies. And here's kind of an example. The flare energy, the very, very weak flares are extremely numerous. They're called nanoflares. And then as you work your way, you know, to higher energy, the frequency of the events falls off very, very quickly, and actually falls off as what's called a power law, which is faster than linear. An inverse square law is a power law, an inverse cube law is a power law, and these all change much more rapidly than a linear equation would predict under the same situations. So that's good news. That means that these super flares are not that common for the sun. However, the historical ones that we have found, you know, they still are troublesome. The odds of seeing another one of these Carrington events within your lifetime, if you're under 20 years of age and you have an 80-year additional life expectancy from the age of 20, basically the odds are about roughly about 1 in 13 that you'll be seeing one of these Carrington events in your remaining lifetime. In the next 80 years, it's about 1 in 13. Or you can round that to 1 in 10. So the point is that, you know, 1 in 10 is arguably, you know, a much higher than 1 in 100. And so statistically, if it's 1 in 10 and it's a random process, you know, you could see something, you know, in the next 20 years or in the next 40 years, depending on what the statistics look like for that distribution. But the point is that you know, we could expect to see another Carrington event sometime within the lifespan of people currently alive, which is kind of interesting. I'll talk a little bit later about what those events would look like. For superflares, if you do the same calculation for superflares, the odds are a bit lower, but it's not dramatically lower. It's 1 in 56 or roughly 1 in 60 that you might see another one of these superflare events like the 1774 AD event in your lifetime. That's a little bit chilling. that means that, if you went to Las Vegas and gambled with odds that were 1 in 56, you'd probably be doing pretty good. If played the lottery with those odds, you'd probably be, you know, guaranteed that within a short amount of time you're actually going to get some winnings. Now, unfortunately, you only have one human lifetime at a time. So 1 in 56 over your remaining lifetime, yeah, probably means that it's unlikely you're going to see anything like a superflare event. But as I said, the odds are still pretty good that you might see a Carrington event. So, it depends on what you're looking forward to seeing before you decide to leave the world. And the way that one calculates this is, through this calculation. It basically, if there were two of these superflare events every 9,000 years, there would be one of these events every 4,500 years. Human lifespan remaining is about 80 years, so the ratio is 1 over 56, and that's where that sort of comes from as an odds. Assuming that the flare is randomly distributed over this period of time and that your sampling during your lifetime is also, on average, not biased in some way. The usual sort of argument you make when you're doing a statistical calculation. So if you do have a superflare in your future or a Carrington event, here are some of the possibilities for what might happen. None of them are especially good. If you have a Carrington event, the length of this would be measured in days, probably up to a week or so. You'd have the partial loss of the Earth's magnetic field, the magnetosphere rather. The magnetic field of the Earth would remain, but it's the space component of it would be completely destroyed and tangled up and distorted. The Van Allen belts, based on the Carrington event, there would be a partial loss, and it would take several weeks for the particles to refill. If you had astronauts working in space, it would be considered a lethal dose for 20% of the astronaut population if they were unshielded. Electric grid, probably a 50% global loss, and that would continue for probably many months with rolling blackouts as people try to frantically replace the transformers that were lost. Geostationary satellites, probably a 50% loss through radiation damage. Low Earth orbit satellites, somewhat less than a 50% loss because they're partially shielded by Earth's outer atmosphere, so that's good. But as you step up to these more powerful events, the 774 AD event and the one way back 12,000 years ago, you're in a completely different category of impacts. The only thing that's basically kludgy is the life expectancy of an astronaut. And I just sort of hypothetically put in LD 50% and LD 100% for these two. I mean, I can't imagine the radiation storm that's going to be present even for the 774 event. And that might very well be 100% lethal for any astronaut, even if they are shielded. But everything else basically is a full loss. But I'd also like you to look at that top line. The duration of the event is months to years, or 5 to 10 years, depending on which of these categories you see. So the environment of the Earth would be remaining very hostile for interplanetary travel or even travel around an orbit of the Earth for a very, very long period of time. We could also look at a few other characteristics here. The ozone layer, total loss in all these cases, and if the duration is months to years, then this total loss will continue for weeks to months at least before it can heal itself through the normal chemistry that goes on. Magnetic field at the Earth's surface, for Carrington event, it's highly variable. We see magnetic storms for the Carrington event that were really dramatic. Compass needles went crazy, telegraph systems went crazy. In the case of the 774 event, highly variable everywhere for periods of months to years, not just days. And finally, for the more powerful, very ancient event, everywhere variable for 5 to 10 years. So compass navigation and all of that would be basically destroyed on the surface of the Earth if you use, well, magnetic compasses. You use satellites, and you could create ones that could survive the environment of these really big superflare events. Then you could still do navigation on the surface, like with various types of satellite technologies. Um, Interesting for the atmosphere itself. There's no loss below 100 kilometers for the Earth's atmosphere. It's for the Carrington event, but there could very well be significant loss of the upper atmosphere for the very big superflare event. In the For the biggest of the biggest events, which we have not experienced since the Earth was formed, we're even talking about the partial stripping away of most of Earth's atmosphere. So it can get really scary very quickly as you start looking at these very, very infrequent events. They're even more infrequent than the one 12,000 years ago. But as I said, looking at the geologic record on the surface of the moon, it looks like our Earth has been pretty calm for the last 5 million years, even considering that we've had a number of these superflare events. There haven't been dramatically more of these superflare events over the last 5 million years than what we can see in the carbon-14 record. So that's good news. There's not this massive, huge flare waiting waiting to affect us over this period of time. But we've seen basically the best that the Earth is able to produce in the last 5 million years in the carbon-14 record that we currently have. Oh, yeah. So the surface ocean life will survive all of this stuff with proper UV shielding, because that's the only thing that gets down to the surface of the Earth is the ultraviolet, and that's shielded by the ozone layer. So, if you lose your ozone layer for a period of time, then you've got problems on the surface of the Earth with, getting skin cancer. Certain types of plants don't like UVB and UVC, which would be coming through. And so there could be problems for plant life on the surface of the Earth on the land, not so much in the water for some of these really big superflare events. Also, you might note that with the Carrington event, we had changes in the Earth's surface magnetic field that were variable in some areas for periods of days or so. That really wouldn't affect navigation of birds and whales and things like that in the ocean. I mean, they could tolerate a couple of day disturbance in detecting the direction of magnetic north using their sensory organs. But if we're talking about changes that last months to years or even a decade, that significantly affects animal navigation using the Earth's magnetic field near the surface. So that could probably be a problem. It might not be an extinction level event for these species. The thing is that we don't notice any changes in species during these big events. So that's a good thing. It means that life basically continues. There might be some problems with convenience and navigation. Maybe certain foods won't be available, but life seems to be adaptable within a species to sort of overcome that. So we don't have, global extinctions of particular species that track with these carbon-14 events. So we think that life survives superflare events, at least the types that we've seen so far from our sun, which is, at the bottom line, is sort of a good thing to know. That even if these things might be in the wings waiting to arrive at some point in the future, there'll be inconveniences. We might lose some of our technology for a period of time, but we will certainly adapt under the new conditions, which won't persist for more than about a typical sunspot cycle anyway. So anyway, that's where we are with the superflare events. Next time, what I'd like to go over is how planets lose their atmospheres, which is a really interesting topic in itself. So, okay, I'm going to stop sharing and I'm going to go back to you guys and you can ask questions.
We've had some discussion of what was survivable. Well, then you got into that. Rowanus she says, I don't quite understand why there would be loss of the magnetosphere and the Van Allen belts with the superflare.
The superflare, if it's like the Carrington event, is accompanied by a massive coronal mass ejection, which is a plasma cloud. And a cloud like the Carrington event cloud did have a measurable effect on the magnetosphere of the Earth. It actually compressed it all the way down to the upper atmosphere and destroyed the Van Allen radiation belts en route. So we know that even a Carrington event is rather disturbing and upsetting for the Earth's magnetic field in space. Now, of course, the Earth's magnetic field doesn't go away because it's produced in the core of the Earth, and that doesn't change. That's not affected. But in between, you have the surface field, and that does get changed quite a bit, but only temporarily for a Carrington event. So yeah, I mean, the Earth's magnetic field will change. It'll be disrupted, turned into basically a garbage can of changing fields and field concentrations and things that we've never seen before. It won't look anything like that nice bar magnet dipole that we all like to think in terms of. It'll be something much, much more distorted and changing over time very quickly. And as a result, there won't be any places where trapped particles can remain trapped for very long. So you won't be able to build up the Van Allen radiation belts during this period.
Matthew, you have your hand up, and I see you've unmuted. Go for it.
So, Dr. Sten Odenwald, have you ever seen the NASA spacecraft called Punch? If you do see one, would it be the easy same target as SphereX?
I can't answer that question. I don't know enough about the two missions to be able to tell you what they're going to look at that's different from each other. So,
and Punch, if you go to their website, they do have a place where you can ask questions, and they're pretty responsive, I understand. So you might try that. And they're going to be launching soon, so they're pretty excited. Okay, another question was just a clarification question. Did you say that you had checked on the impact on other planets of the solar flares?
No, I hadn't talked about that. No.
Okay, that would be interesting, though, huh? Gerald, are you raising your hand?
Yes,
Yeah,
yes.
I mean, for Venus, Venus has such a thick atmosphere that it's not really going to be affected too much. Mars, that's problematic. I mean, it has such a thin atmosphere and no magnetic field that its remaining atmosphere would be stripped away by one of these superflare events. But beyond the orbit of Mars, basically, there's no real significant change because now we're talking about, the gas giant planets, which have extremely strong magnetic fields and are very stiff compared to what a superflare would produce. So really, it's only Earth that really gets mangled by one of these superflare events.
Gerald, do you want to jump in with a question in our last few minutes?
Yes, yeah. Sten, thanks again for a wonderful presentation. I've been waiting for years to learn some of this. There are two quick questions. Number one, a takeaway is if someone asked if we had any warning, and if we did, it sounds like we should jump into the ocean. Did I properly take away that from your talk? And then the second part, though, is being an amateur radio operator, I've always looked at the Carrington event as like, I don't want to be doomsday, but this would destroy our modern world. Now, some people say the switching systems are hardened more these days and so forth. But would you mind talk a little bit about that? Just what would be on the ground effects we would see?
Well, for a superflare event that's more powerful than a Carrington, I mean, we're talking about a dramatically different level of destruction.
Yeah.
It's almost hard to know where to begin. Well, first of all, we don't exactly know what these superflares look like. We don't know what their magnetic fields are. We don't know their plasma densities and specific things like that. All we know is that they carry an awful lot of energy because we see them through the light that they produce on these Kepler stars. For the Earth, we do have a small sample of superflare events from the carbon-14 record, and we can work backwards from the carbon-14 anomaly size to get an idea of their energy. But again, we don't know the intensity of the magnetic fields involved, the plasma density and interplanetary space and things like that. So it's something of, kind of a guesstimate. But we do know how they stand in relationship to the Carrington event. And so if we do a simple scaling based on the energy, then we wind up with some very dreadful looking things. We would have difficulty surviving another Carrington event. Estimates for satellite damage range from losing a third of our geosynchronous satellites from radiation damage, loss of many, if not most, of our LEO low Earth orbit satellites from anomalous atmospheric drag, because the heating of the Earth's upper atmosphere would increase the friction and deorbit a lot of these things, even above the orbit of the International Space Station. So the good news is that the SpaceX satellites would no longer be a problem for photographers on the ground. But I wouldn't hold your breath for waiting for that event to take care of things. Now, the changing magnetic field of the Earth, because this is a massive cloud of plasma with a magnetic field in it, would produce ground currents that would basically fry every transformer on the planet, not just the big ones, but also the small ones that are grounded like many transformer circuits are. So we would lose our power grid. And that, and we would lose it for probably many years. So that a superflare is a devastating event. If you then look at what happens to ultraviolet fluxes on the surface because you lose your ozone layer, or you've basically lost your ionosphere for radio communications, you don't even have reasonable backups losing your satellites in the radio, ground-based ham radio regime. So but as I said, our sun seems to be now old enough. It's now matriculated into being an older star. So there are statistically much fewer of these really super Carrington events going on. I mean, we've had, a few, one every few thousand years, which, is probably tolerable. But even so, one of these is not something to be trifled with and will cause, quite a lot of damage when it does arrive. Now, also, the radiation pulse that comes from this, because it's going to be a massive accelerator of protons to very, very high energies, just like all CMEs are, you're going to have astronauts that will be receiving lethal doses of radiation, no matter if they're inside their bulkhead or outside or whatever. Now, warnings, what you have to think in terms of is that these big superflares don't just spontaneously come off of the surface of the star. There are conditions that are preludes to this. There must be massive sunspots that are almost, a third the surface area of the star in size. We would be able to see a sunspot a third the surface area of the sun facing us, and we would know that there is something dreadful about to happen. But right now, we don't see sunspots nearly that big. We only see sunspots that are about a tenth the size of one of these superflare events. So I think as a warning, we would have probably a week's warning seeing one of these large sunspot groups, a third the area of the sun, rotating into the Earth-facing hemisphere. And then we'd know that, okay, that's it for us. So we'd get a week's warning, which is actually longer than what we get, for coronal mass ejection halo events. They only give us about a 3-day warning. So, that's the good news. And we won't have to worry for one of these superflare events, whether it's on the edge of the limb of the sun or directly at the center facing the Earth. No matter where it is on the Earth-facing hemisphere of the sun, it would be a bad thing.
Thank you.
Yeah.
Well, thanks everybody. We're out of time, but if you have additional questions, send them to me and I'll put them in with when I send you the recording link. So It's nice to see you all, and hopefully we'll see you next month.
righty. See you later.